Hello, everyone. Welcome to pre-lecture 19. So this is going to be our first pre-lecture in chapter 15 of our textbook, and we're going to be starting solubility equilibria. That's going to be our last equilibrium chapter for the semester, which I'm sure you are sad about, but we'll enjoy it while we can. Okay, so hopefully you remember from Gen Chem 1 that the solubility of a substance can vary from essentially 0, so something that could be insoluble, to essentially infinity. So if you think about something like water and ethanol, those are two miscible liquids that are, because they are miscible, we would say their solubility in each other is essentially infinite. And that's great. However, this chapter we're going to be focusing on things that are sparingly soluble. And so consider, for example, silver chloride. So silver chloride, according to the list we gave you in Gen Chem 1 of things that are insoluble, silver chloride was one of the compounds that is insoluble. But in reality, it's actually an equilibrium between silver plus and chloride minus. And so we can actually define that as an equilibrium that we can quantify. And this is something that we call solubility product equilibrium. And so we get our K value, we designate this KSP, SP for solubility product. And of course, we can write our chemical equation. If we do products over reactants, we get our products, Ag plus, Cl minus, and then you'll notice that silver chloride, the solid, is a solid, so we don't include it in our equilibrium expression. Okay. So let's say you were going to write KSP expressions for these. I would recommend taking a moment to do that yourself. I will go through them here. So say we start with the solids, magnesium hydroxide, and then calcium phosphate hydroxide. And so each of these are different salts. And so if we think about magnesium hydroxide, the way you start KSP problems, similar to all of our equilibrium problems, is start with our reactant. In this case, for all of our KSP problems, our reactant is always going to be a solid. And so hopefully that's helpful. Reactant will always be a solid, and it'll be in equilibrium with the ions that it dissociates into. So if you look on the periodic table, you can see magnesium in the second column. So it'll be Mg2 plus, and then we get 2 OH minus, right? So we don't get OH2, that's not a thing. Hydroxide is OH minus, which hopefully we know well by this point because of our acid base unit, and because we have 2 on our reactant side, we end up with 2 on our product side. Okay, and so if we were to write the KSP expression, then KSP is equal to our Mg2 plus concentration times our hydroxide concentration squared, right? Because we have this 2 again in our products. A reminder that products over reactants raised to their powers. Okay, that would be magnesium hydroxide. Calcium phosphate hydroxide, this is actually what our teeth are made up of. So our teeth are a mineral, and we usually call it enamel. So this is actually what enamel is on a chemical level. And so we say that that starts as a solid. Again, KSP, we're always starting with solids. And then this is what we would call a complex ion, where we have calcium phosphate. Then we have this hydroxide that we can actually break off and be in equilibrium with. So we can end up with Ca5 PO4 3 plus, right? That'll be aqueous. And then we also have OH minus. It'll be aqueous. Okay. So same thing. If we were to write our equilibrium expression, our KSP is going to be our products over our reactants raised to the powers. But in this case, our powers are going to be just 1 for each. And so we don't need any exponents. This is also the process by which your teeth decay. So if you lose this hydroxide, your enamel starts dissolving, you'll lose that hydroxide. And when we use toothpaste or drink fluorinated water, what we're actually doing is replacing this hydroxide with a fluorine that is much more inert to things that are acidic. So that's a little connection for you today for those of you that may want to go on to dental school. This is the chemistry behind fluorination for our teeth. Okay? Anyhow, that would be writing KSP for our different salts that are sparingly soluble. Okay, I'm going to clear those and we'll keep going. So oftentimes what we're doing with the KSP is relating how it's measured to the solubility of how much it dissolves, including dissociation and solvation. And so generally speaking, again, anytime we do KSP, we're going to start with a solid and end with some sort of dissolved ions. Those dissolved ions will be raised to their powers. Because our reactant is always a solid, that means that we don't need to include it in our KSP expression, right? And so our KSP value can be determined from the equilibrium concentrations of our products, or we can determine their concentration at equilibrium if we have KSP. And so as with most things in Gen Chem, you will have all of the variables but one, and you'll need to find the one that you don't have. Okay. So let's give that a try. In this example, we have magnesium hydroxide back here, and the KSP value is 5.6 times 10 to the negative 12. And so I ask you, what is the molar solubility of, and I put calcium hydroxide there. Of course, it should be magnesium. And so I will fix that in the PowerPoint. But we're going to be working with magnesium hydroxide here. And so if we start by doing the two things, I recommend for all equilibrium problems, write the relevant chemical reaction. So KSP, we're always starting with the solid, and then it's going to be in equilibrium with our ions, so Mg2 plus and 2OH minus. Then our KSP expression that we had already done was KSP is equal to concentration of Mg2 plus and OH minus squared. So good news, we can use our favorite tool, our favorite chart of any chart we've ever used, ice chart, right? And we don't need to include our solid, our magnesium, and our hydroxide. We'll start with concentration of 0. We'll have X plus X, and this is, again, after acid bases, just a reminder, when we dissociate two hydroxides, it'll be plus 2X here because we have a 2 coefficient, and this will be X and 2X, right? Then if we plug our known numbers, basically, or variables into our KSP expression, we should get 5.6 times 10 to the negative 12 being equal to X for magnesium times 2X squared for our hydroxide. And so if we do a little consolidation there, 5.6 times 10 to the negative 12 equal to 4X cubed. The way I got that is our squared goes into both our 2 there, so that's where I get the 4. Then we have x squared times x is x cubed. And if we divide each side by 4 and take a cubed root, we should be able to get x. And so the value for x I got was 1.12 times 10 to the negative 4th. That is equal to, if we again look back at our ice chart, X is equal to our concentration of magnesium. So this is equal to concentration of magnesium And then if we want to find our concentration of hydroxide, that is equal to 2 times x. And so we would do 2 times 1.12 times 10 to the negative fourth. And so that is equal to 2.24 times 10 to the minus fourth for our concentration of hydroxide. Okay, then that is our concentration of magnesium. Right? Hopefully that made sense. If it didn't, please ask me before lecture whenever you're watching this. Okay, right, and that is it for the pre-lecture video today. I hope you have a KSBSL day. If you have any questions, please let me know. Otherwise, I will see you in class.